Next, we're going to talk about MLPerf Storage. I'm David Cantor. I'm one of the founders and the head of MLPerf, and I'm with
Curtis Anderson, one of the co-chairs of the MLPerf Storage Working Group.
Yeah, and so this is a community effort. And so I'm going to just give one brief introduction, hand it over to Curtis to talk about the work of the community. But really the motivation for MLPerf Storage is up in this slide here, right? And so this is data from Meta talking about the growth in the use of storage for AI training. And what you can see is over 8 quarters, they essentially doubled the amount of storage they needed, the amount of data they needed to store, but the actual ingress bandwidth, or sorry, I guess egress from storage, ingress into compute, has grown even faster than that, right? And so storage is truly critical for our big data models. So why do we want to measure storage? Curtis, why don't you take it away?
Thank you. To make use of AI, you clearly need accelerators to do the training. You need networks to communicate the data from storage into the accelerators. There's a bunch of different pieces that go into that. So full system performance says, I need to know what storage is capable of. From the point of view of the benchmark, we're trying to produce a relative comparison for the people who want to acquire storage for use in an AI environment. But we're also trying to help the people who build the infrastructure, like PyTorch and TensorFlow, those kinds of frameworks, to optimize for storage systems. As you can imagine from the majors that are training the foundation models, there's an enormous amount of data, an enormous number of accelerators, and that means an enormous amount of bandwidth and capacity to manage for the storage system to manage. So it's about an informed decision for the purchasers. It's about the researchers who are trying to build better storage systems, and it's about the product vendors who are building storage systems who want to optimize for the AI workloads.
Hey, Chris, I mean, most of the storage for AI training is typically direct access storage or something like that. It's not necessarily network storage.
Actually, the vast majority is network storage, because the fundamental thing that causes fits for the storage people is the data access pattern has to be random. You can't feed the data, you can't show all of your cat pictures and then all of your dog pictures, because the neural network won't learn that way. You have to intersperse them randomly. And so you go through one epoch feeding the data through, and then the next epoch has to be a different pattern. And so that defeats all of the normal caching techniques that storage systems tend to use. And in general, the amount of data that most people have is much too large for any in-node storage solution. So generally, most storage is actually external, outside the nodes.
I guess I agree with respect to capacity, but the data coming into the GPU, you think that's typically off the network?
Yeah. And that's one of the challenges, right? The storage system providers are working hard to figure out how to make that work better than you might. Oh, well, why would that work well? Well, but yet that's one of the requirements. And so,
I mean, like GPU direct and things of that nature. Is that
sure?
Yeah, because we're not talking about like traditional network attached storage necessarily. I mean, I think we're talking about all sorts of exciting new solutions for network storage. So yeah, we've got GPU direct. Yeah. Obviously, we've got a lot of parallel NFS going on in there. We've got a lot of object storage, scalable, scale out object storage solutions being used. I've even heard about things like S3 over RDMA, and
yes.
Obviously InfiniBand is in there. So yeah, it's not like traditional network storage, but like, I mean, the thing that kills me when I see graphs like this is, we've never designed storage systems, right? I mean, we never designed these things to be able to have twice as much I/O as they were designed for, yes. Per unit volume. We've never designed them to be able to handle this kind of randomization or this kind of parallel access. It's just not what we were making storage for generally. But I think like folks like you were actually making storage like that, like with Panasys and so on, where storage for HPC is more applicable to what's happening here with ML than traditional corporate NAS.
Right.
I don't want to put words into your mouth.
Yeah, no. That's all fair. It's a good summary.
Yeah, but I totally put words in your mouth. Okay.
So Storage is a slow-moving business in terms of architectures, right? The quality requirements are so high. If you lose data, you're toast, right? And so the quality requirements are high enough that people don't take large risks unless they need to. And so that's what's happening with AI is the industry is being forced to take larger risks, do more innovation, increase the speed of innovation in order to meet the needs, right? And so that's one of the interesting, exciting things about it is storage wouldn't change unless there was a driver that forced us to change, right? Because of the quality that we have to do.
That's actually a really interesting point because things have changed, like what we want to do with the data and how we're going to process the data. So the storage, the access to storage, access to data within the storage systems has to change with everything else. We've just come to that point.
Right. Yeah. I mean, tapes didn't die. Hard drives will never die. SANs will never die. They'll shrink and they'll be fit for a particular set of use cases. And so now AI is taking over. It's on every storage vendor or supplier's top of the list, saying, okay, how do I play in this exploding market? Right. And so what do I need to do to my product to best serve the needs of that market?
Of course, this is for training, though, but there's also inferencing and other, RAG and other elements of storage as well. They're going to have completely different access patterns.
Absolutely, that's completely different. So
you're not addressing that with with the storage performance yet.
We are in the process.
Okay.
So let me. Okay. So I'll go through the techniques of what the benchmark does here, and then, but to directly answer your question, we support 3 workloads today: UNET 3D, ResNet 50, and CosmoFlow in the version 1.0 of the benchmark, and those each apply a different workload to the storage from each other. Some of those run under PyTorch, some run under TensorFlow, and the TensorFlow versus PyTorch are also very different workloads applied to storage. And so the
training versions of those, right?
Those are training versions, yes. Now we're in the process of working through a RAG pipeline, so a large language model with a vector database underneath, and the database, it has yet another different workload. The challenge with inference is, in general, there's not much data involved in inference, except for possibly in the RAG pipeline.
It depends, right? What your point of context is. There is a lot of data from some traditional client application standards, but not much data compared to training.
Not much compared to training, but and it's a singleton, a one-off, right? You say, okay, here's an X-ray analyzer.
Here's the data,
right? Yeah. And so the
it's indexed too. RAG is indexed, and
RAG is
There's a lot of sort of now in context RAG, like get all of the chunks compared RAG, which that changes from traditional RAG even to CAG, what they're calling context. Anyway, so I'd love to hear all about that. I think would be incredibly interesting.
It is interesting. We're just starting down that. That'll be we're targeting that for version 2.0 of the benchmark.
Okay.
Our best guess at the beginning was that normal inferencing wasn't interesting from a storage perspective, wasn't challenging to the solutions out there. Vector database, we're getting farther into it, and in a chat kind of context, the amount of compute time is very large compared to the amount of I/O time to do the RAG lookup, right? But things are changing constantly, right? And so we're tracking.
Ref, RAG, CAG, again, all the
right.
So in timelines, we saw the prior list of like the benchmarks that started and when they came before, and the ones that were deprecated and became the dash lines that Ray didn't like. Within this world, we've heard about storage arrays that have been created and solutions and storage architectures have been created. You're probably chasing just enterprise workloads, go chase the biggest market, optimize for this.
Right.
Synthetic benchmarks that made you as a vendor look better or worse compared to, Where would you say we are maturity? I know you're saying we're just getting started, but maturity-wise, are you starting to see specific vendor adoption of these in their marketing collateral or stories they're telling to the market about how they're performing using this benchmark?
Yes.
Okay.
I don't know if I have a slide on it, but I'll just tell you. We had a version 0.5 release, which is sort of the traditional proof of concept thing that MLCommons does.
0.5, not a 1.0.
No. That was the first one. Everybody does 0.5 to say, okay, we think we can make a real benchmark out of this.
Okay.
And then we had a 1.0. The 0.5, we had 4 submitters and 20 submissions, or maybe it was 30. And now, then we went to 14 submitters and 105 or 130 submissions, right? So the ramp we think is very steep. I'm getting a lot more interest in organizations wanting to join the working group in order to post this, right? AI is an enormous market, and it's the new hot markets where all the investment is going. And so the way I describe it, 10 years ago, every CIO said, what's my cloud story? Now, every CIO and every other C-level executive saying, what's my AI story? It's a much bigger wave, right? And so all the storage vendors will respond, right? So yeah, I'm expecting that the growth of the use of the benchmark will continue, right? And we're also intending to help the product organizations optimize for this workload. But that was one of the things that we had to do in our 0 to 5 is, well, what is the storage workload that comes from AI training? And it's very different from most other things. It's not a database or a streaming workload or anything else.
And there was a trend years ago that if you were a storage engineer, your career is over. You need you need to become a cloud engineer because cloud.
Oh yes.
So do you anticipate a similar, like, if you're still a storage engineer and you didn't quite make it to being a cloud engineer, just forget that, go straight to AI engineer. You know,
Yes.
Maybe it's out of your wheelhouse, I don't know, but what's your thinking on these kinds of, like, you know, your career, your title is dead. You know,
Oh no,
it's moved.
I started storage 40 years ago, and my kids go into computer science, and I said, no, don't do storage. It's over, right? And now it's not again, which is very cool.
Yeah.
So,
Cry.
so let me describe a little bit about the structure of the benchmark, and then we'll go into what the workload looks like. So in the normal environment, you've got your data set on storage, you've got system memory, you've got the accelerator on the far right, and then there's some online pre-processing. So let me define what that is from a storage perspective. I've got a certain amount of, I'm going to use cats and dog images just because it's easy, right? I got a bunch of pictures of cats, but more data is generally better. So I can take that picture pull a cat picture in, and then I can rotate it 15 degrees. Still a cat now, but the neural network sees this as a different image. I can change the color palette a little bit, right? So that's data pre-processing. It multiplies the effective amount of data, and I get a higher quality resolution of predictive ability on cats. So that's the structure that we're trying to model. What we're doing, because we're only interested in the storage piece, is we've got the storage. It comes into system memory. We don't need the accelerator. We just put a sleep in there saying, well, the computation time for this type of data by this accelerator on this workload is 327 milliseconds per batch. And so we just sleep and we're just pulling the data into memory, and we're ignoring all the other things. That's sufficient to stress the storage out.
Why burn down the rainforest when you don't need to do it?
Absolutely. Well, and as you know, the accelerators are expensive, and so the storage vendors don't really want to buy 150 of those if they don't have to. Right?
Have any of the vendors of those cards that do that, have they tried to influence, like, no, really, we need to bring in it needs to be real traffic, not synthetic traffic. Anything you've heard in that space?
No, the suppliers of accelerators, I say accelerators because I'm trying not to, I really want the non-NVIDIA people to also participate, right?
Yeah.
We have some NVIDIA people in the working group.
And there's all kinds of custom silicon that's going on in
Yes.
other places too. So, okay,
Yeah.
very good.
So significant variables, and then I'll go through, there's a couple more I need to add to this. The framework, PyTorch versus TensorFlow. PyTorch, generally speaking, if you got images, for example, cats and dogs, you're going to have a directory tree full of files. Every file is a single image. With TensorFlow, it's much more like a tar file for people to know storage, right? So you put a whole bunch of images, like 1,000 images into a single file. From the storage perspective, to get a single data point, a single image, I have to do some directory lookups and a file open and a whole bunch of traversal metadata operations. TensorFlow, I just read the next image out of the already open file. So vastly different workloads from the point of view of the metadata and data operations of a storage system. Storage network, how we're connected. we've had several submitters realize a little late that lossless networks were required. So you get a TCP packet dropout, and then all of a sudden your storage performance goes to the floor because you're waiting for retransmission. And so there's nuances that are interesting about the storage networking. The solution, hardware and software, how it works internally. Is it an HPC class parallel file system? Is it, lots of different things.
Chris, I saw one,
Sure.
I think it was version 1.0 that had an SSD vendor submit SSD versions of submissions for MLPerf storage. So,
Yep.
Yeah.
I got 3 minutes left, so we got to keep moving. It's valid, right? We're trying to bridge that dynamic or range from single SSD vendor all the way up to 1,000 node HPC submissions, because we Argonne National Lab submitted.
Intense pulse neutron source.
Yes. Type of training, distributed training, the single host, we started with that. Then we moved to what's called data parallel training. So data parallel, the way I describe it as a storage guy, is every accelerator has the complete model, and you're going to pass a shard of the data across that model, and they periodically exchange weights. Model parallelism, as opposed to data parallelism, every GPU or every accelerator has a shard of the model, and you're going to pass all the data past every one of them, and then you exchange some weights. So we're doing data parallel caching. So here are the workloads. There are different categories, like image segmentation, image classification, scientific cosmology. We're looking at a RAG pipeline. We're looking at checkpointing. For large language model training, you have to take checkpoints because the training will last for a month or two, and you can't afford to take an outage in the middle and lose all of that. So I wanted to go through, storage. 13 organizations, 100 results. Here are the organizations that submitted. So I'll leave that up for a second. Well, some structure about the benchmark proper. So the thing we wanted to say is, or we were trying to demonstrate, is the storage is not going to slow down the compute. So that means that there's a request from the framework, say, I need these data points. I need to pull them into system memory before the current computation is finished in the GPU. Otherwise, the GPU goes idle. Those things are expensive. Nobody wants those to go idle. So we have a metric of accelerator utilization, which is AU%. Is that we have to keep the accelerator 95% busy. So if you have excess latency on some I/O operations, that counts against you. Too many of those, and you don't have a valid submission any longer, right? It's keeping the thing busy is the sort of the core metric. Can you keep up with the demand? We also have two categories, open and closed. Closed is apples to apples comparison. It's virtually identical workload from all submitters, no innovation, no changes. Here's the baseline, can you do it? Open, on the other hand, is for the submitter to say, here's my close number, but now if you're willing to make these changes in your environment, look what I can do for you, right? So they're not comparable against each other, but it's a place for the innovation to happen, right? This training has a similar structure, a little bit different with open and closed. Oh, here we go, open and closed. So these are the submissions from the 1.0. Only one organization chose to do open, mostly because almost all of these were new. We only had 4 submitters in 0.5, and so they were all.
Are you working with any RAG vendors right now? And if you are, can you mention who they are?
We haven't yet decided. The current proposal is that we pick a representative RAG solution and a vector database, and then that's the standard workload that everyone applies in a closed.
But they vary, right? You got your Postgres, you got your Docker.
They do, and so
you got your fat files. So anyway, that's why I'd asked the question.
Right. Currently, we're proposing to have one.
Okay.
Right, because this is a crawl, walk, run structure. Key insights, and so we're down to the last 2 slides. 48 seconds. I can do it. Explosion AI micro driving a wave innovation. Said that before. stability. Lots of different architectures out there are coming out because people are saying, "Oh, I had this odd little architecture that wasn't getting a lot of market traction, but look, I can do a really good job on this benchmark. I think I have a shot at large growth opportunity." Yes. Listening results. It's important to know that for storage vendors, this is new territory, and so they're doing a lot of work to understand what the workload means. Where is my architecture stressed by this workload? And distributed single host scale of different frameworks. Yeah. So there's a lot of challenges.
It's that last bullet I think that stands out. You know, it is you go to your old spec websites and you work for or you're purchasing that next box from that next storage vendor, and it seems like you're going with some arbitrary thing that someone says they've optimized for.
Right.
In this one, because it is community, because it is transparent and traceable.
Right.
Do you think people are going to make better IT purchasing decisions because of the existence of this?
Yes, because the data scientists, they are focused on their neural network architecture. They don't care about storage and networking and all the rest of that because the innovation is coming with the neural network architecture.
Yeah.
Right. That's the value. And so they say, whatever, fix me up with something that's going to work for me. That's the measure of what's going to work for them. Right. And so that's our goal, at least, and we think it's working.
So, the thing I find interesting, I'm more of on the data engineering side and database administration side, and, all the stuff that you have to do to feed not the GPUs, but the developers.
Yes.
I just find it fascinating. Just popped into my head that, even 10 years ago, we were freaking out if a CPU was overtasking, and now we're worried about GPUs that have to be fed all the time. It's just interesting to see how things have turned inside out. For people that are in the industry, in the trenches, trying to figure this stuff out, do you see that a standard like your standard, for auditing for accuracy would be useful below the CTO or C level for people in the data engineering and database administration space and even application development space?
Absolutely. The storage system architecture is one piece of the puzzle, right? And so in order to, if you don't measure it, you're not going to improve it, right? We're measuring the architectural performance. Here's a set of gear, and what performance you're getting out of it in terms of batches per minute, right, or whatever, right? The AI metrics, right? And so that's driving innovation there. But the vector databases are also brand new, and so they're going to go through their own shakeout in terms of who's got the better architecture and the better performance.
Right, and even things like different vector indexes,
absolutely,
performance, depending if you're doing approximate or exact searches, there's all kinds of things like that. Yeah,
right.
Good point.
Cool.
All right.
If I could just make a comment.
Go ahead.
So first of all, this is fascinating. I had heard about your work before. I was strangely particularly grabbed by your discussion about PyTorch versus TensorFlow. I think there is such a massive imbalance in the way people think about AI. It's like all GPUs, that's everything, and maybe this model and this 3 billion and trillion things like this. When there's so many really critical, important considerations, right? Like storage, like file systems, like things like this.
Yes.
And I say that in a sense of, many of us talk to other people as we have to nudge and educate and just make the discussion much broader.
Oh, yes.
Than I really think it is with AI, because these considerations are just paramount. And they completely clog up all this wonderful processing that's supposed to be.
Totally.
I mean, David Cantor said it earlier that it's a whole system problem, but it's a whole system problem to achieve the results that people want. To keep the accelerators busy, you need networking and storage and orchestration and on and on and on in order to make the thing work. To get the best efficiency. I mean, at the price of NVIDIA accelerators and GPUs, right, that's a resource you really don't want to be idle.